All right, I'm gonna try to do one more video here in my marathon recording section. I want to finish 11.6 by talking about the root test. The root test is very similar, at least in idea, to the ratio test. It's just you're checking a different limit. It's the same kind of thing where you look at a specific limit, and depending on the outcome of what the limit is, it tells us is the series absolutely convergent, divergent, or is the test inconclusive. So here's the root test. We have a series. We look at, or suppose the limit of n approaches infinity. Well, with the ratio test, we looked at the limit of ratios of consecutive terms. For the root test, we look at the limit of a certain root. It's the nth root of an, and to make sure it works, as n changes, sometimes this is a square root, sometimes it's a fourth root, even root, or odd root. To make sure it works for all n, we have to put absolute values around the an to make sure the inside's positive, so the root makes sense. We look at this limit, and we suppose that it's equal to L. Again, just like with the ratio test, it could be infinite. That's valid. So L could be infinity. And so we compute this limit, and then depending on what it is, what its value is, it tells us absolutely convergent, divergent, or inconclusive. The conditions, the three cases, are exactly what they were for the ratio test. So if L is less than 1, the series is absolutely convergent. If L is bigger than 1, you have divergent. And if it's exactly equal to 1, it's inconclusive. So the test is virtually identical to the ratio test, except the thing you're taking the limit of is different. For the ratio test, it was a ratio. For the root test, it's this root expression. All right. So ratio and root test are kind of a pair that they go together. It's always the case. So if you're presented with a particular series and you want to figure out is it convergent or divergent, and you know you want to use either the ratio test or the root test, depending on the specifics of the series, one may be better than the other. One may be easier than the other. But if suppose I try to do the ratio test and I get inconclusive, then the root test would also give me inconclusive, and vice versa. If I try the root test first and it gives me inconclusive, the ratio test won't work either. It'll give me inconclusive as well. So they're pretty much equivalent. If one of them works, the other one works. If one of them fails, the other one fails. So it's just a matter of which one is easier to try. If you try it and it fails, then don't bother with the other one. So let's look at some examples of when the root test is convenient. And let's illustrate the root test. So in some sense, it's kind of easy to recognize when the root test is a good idea. So let's look at this. 2n over 5n plus 3 to the nth power as n goes from 1 to infinity. All right, so this one, we know we're going to use the root test, but why is it a good choice? Well, it's when you have an n in the exponent, and you also have n's in the base. I might be able to do a ratio test on that, but it would be a difficult ratio test. If there's n's in both the base and the exponent, ratios would be a pain. But as we'll see, the root test, I would need to take the nth root. I don't need that much space. I need to take the nth root of the absolute value of this. This is positive, so I don't need to worry about absolute value. Nth root of an nth power, those cancel. So if you want to generalize, how do you simplify an nth root? You're just dividing the exponent that's already there by n. So n divided by n gives me 1. This is going to be the limit then of 2n. Really, here I should put the absolute value. After you do the nth root, make sure you have absolute values. That'll be relevant in many cases. The limit of 2n over 5n plus 3, that's just 2/5, because the degree is the same on the top and the bottom. So 2 over 5. And now you look at that answer, it's less than 1. So the root test tells me absolutely convergent. All right. So let's do another one. So another basic one would be maybe 4 minus 3n divided by 2n plus 1 to the let's say 3n power. Yeah, that's fine. So again, the clue here, if we didn't already know we're using the root test, the clue is we have an exponential expression where n, the variable n, appears in both the exponent and in the base. So that suggests we want to use the root test, because the root test immediately takes an nth root. It's going to at least help with that exponent. It may not completely solve that and make that exponent disappear, but it's going to help with it. So we're taking the nth root of the absolute value of this expression. You can put the power on the absolute value if you want it to make it easier. So like I said before, taking the nth root divides the exponent by n. So we're going to get absolute value of 4 minus 3n divided by 2n plus 1 to the third power. 3n divided by n just gives me a 3. Okay, so now, what's the limit of this? Well, I don't have to cube everything, because we can take the limit of this base and then just cube it. So this base is rational. It's n over n. So it would give me the absolute value of negative 3 over 2 cubed. Absolute value would give me 3 over 2 cubed. That's 27 over 8. 3 cubed over 2 cubed. 27 over 8 is bigger than 1, so this is divergent. Okay. Um, let's do another one that's a little bit worse. So maybe n squared plus 1 divided by 3n squared plus n plus 5 to the power 2n plus 1 as n goes from 0 to infinity. Okay, so this one's a little bit worse, but the same principle still applies. My expression has n's in the base and n's in the exponent. So if I do the root test, we're taking the nth root of this thing and when I take the nth root with this power, I'm dividing an n. I'm dividing this power by n. So my expression becomes this horrible rational expression to the power 2 plus 1 over n. Okay, so I still have n's in the base and in the exponent, but now hopefully we can figure out what this equals. Okay, so as n goes to infinity, let's think of it in pieces. The parentheses part, that's a rational expression with n squared divided by n squared. That parentheses, as n goes to infinity, is going to approach 1/3. The exponent, well, 2 is going to be 2. 1 over n, as n approaches infinity, that's 0. So I get 1/3 squared, which is 1/9. 1/9 is less than 1, so we have absolute convergence. Okay. So I think it's worthwhile here to just briefly remind you about limits of power situations, or the different power forms for infinity. Okay, so when we apply the root test, when we use the root test and we apply that nth root, it's still possible that we might have n's in the exponent. So it's worthwhile here to review some of the different kinds of forms you can get when you take a limit and there's both the base and the exponent are changing. So let's first review what are the indeterminate powers. Indeterminate powers. So there's 3 of them. If the base approaches 0 and the exponent approaches 0, we don't know what that equals in general. You have to do a L'Hopital's rule tricks for these indeterminates. If you have 1 to the infinity power, we don't know what that is, because depending on how the base is approaching 1, if it's approaching from below, you have numbers that are less than 1 being raised to the infinity power. That's going to be 0. If it's approaching from above 1, then you have numbers that are bigger than 1 being raised to the infinity power. That's going to be infinity. So this could be, this wants to be 0 or infinity, but it could basically end up being anything because of those two conflicting urges. The third is infinity to the 0 power. So infinity raised to the 0 power. Okay, because a base approaching infinity wants the whole thing to be infinite, but if it's approaching 0, the exponent's approaching 0, that makes the whole thing want to be 1. So these three situations are indeterminate. You can't figure it out just from the form. You have to do the L'Hopital's rule stuff. So if it helps, you can go back and review the chapter on L'Hopital's rule if you come across these. We're not going to be doing any that are too difficult here. But other powers, other limits involving powers, if it's any form other than these three, you can figure out what the answer is from the context. So, for example, if I have C, which is bigger than 1, and I get C to the infinity, that would be infinity. If C is less than 1, and I have C to the infinity, that would be 0. Infinity to the infinity would be infinity. Things like infinity to the minus infinity power, that would be, 0? Because that negative infinity puts everything in the denominator. Negative exponents put in the denominator. Anything else to the 0 power other than 0 or infinity is going to be 1. And so on. We can figure out any other situation. If it's not one of these three types, any other combination of base and exponent, we can figure it out from the context. So the point is, when we use the root test, we like to use the root test if there's an in both the base and the exponent. When we apply that nth root, it'll help us with the in and the exponent, but there still might be some in's that appear. Like on the last example we did, we had 2 over n remaining. All right. All right, so now let's talk a little bit about strategy for how to approach a series. If the question is, here's a series, does it converge or diverge? And that's all you're asked. Or maybe you're given a little bit more choice, a little bit more of a hint. But how do you determine what's the right strategy to use for that series? So first, let me summarize some of the thought process behind choosing between root test and ratio test. Like I said before, if one of these doesn't work, if one of them gives you inconclusive, then the other one will always give you inconclusive as well. So if one of them works, the other one will also work, but one of them might be easier than the other. So root test, this is good, like we've been saying repeatedly now. If n appears in a base and its exponent. So things like n to the n, or more complicated, or other things like that are more complicated. There's an n in the base and an n in the exponent. I guess it would also work if you just had like a geometric series where you had an r to the n. It would work, but it's way more than you'd need. The ratio test, it handles factorials very well. It also handles exponential functions like r to the n very well. Now, you could easily make up a series that involves both of these things, factorials and n to the n kinds of issues. In that case, there's not really a good answer to which is better. They're both going to have difficult issues. I'd probably default to ratio test, especially there's factorials. I'd rather deal with one of these with the ratio test than try to deal with a root test involving factorials. But that's just myself. I haven't thought about a general strategy for those. These are just guidelines here. So let's do a couple more where I don't tell you which test we're using. So, same question. Here's a series. Does it converge or diverge? -1 to the n times n factorial over 2 to the n squared power. That's 2 raised to the power n squared. Okay, so this one's fairly straightforward. That n factorial suggests ratio test. 2 to the n squared. That might tempt you to use a root test, but you don't need a root test because there's no n in the base. All right, so I'll use the ratio test. And for the ratio test, we're doing the absolute value, so that -1 to the n won't matter. I want the n plus 1 version of our term. So n plus 1 factorial divided by 2 to the power n plus 1 squared. Then we multiply that by the reciprocal. 2 to the power n squared over n factorial. Okay, so now let's group things together according to their type. The factorials go together. N plus 1 factorial divided by n factorial times 2 to the n squared over, let's multiply this out now, 2 to the power n squared plus 2n plus 1. Now let's cancel. N plus 1 factorial over n factorial. The top is bigger. It has one extra factor. So I'll have an n plus 1 left on the top. Now we have 2 powers of 2. When I cancel, I lose the smaller power. So n squared is going to get canceled. So I'm going to lose the 2 to the n squared here. I'm going to be left with 2 to the 2n plus 1. Now, let's skip some work here. I want to find the answer to this limit. I have a linear function divided by an exponential function. The formal way I would compute this would be L'Hopital's rule, but let's just wave our hands a little bit. The denominator is way bigger than the numerator. An exponential function grows way faster than a linear function. So as n approaches infinity, that denominator is going to overwhelm the numerator, and this is going to give me 0. Okay. Again, if you don't believe me, you can use L'Hopital's rule on this. This is infinity divided by infinity. So L'Hopital's rule would give me 1 divided by the derivative of this exponential, which is still going to be exponential. So 1 divided by infinity, which would be 0. So 0 is our limit. 0 is less than 1. So that tells us this absolutely converges. All right, let's do another. Okay, so we want to have the summation of 1 plus 1 over n to the n squared power. I need to start with n equals 1 for that to make sense. All right, so make our choice on how to evaluate this, how to analyze this. There are n's in both places. That suggests we need to use the root test. Again, it doesn't mean that ratio test wouldn't work. It just suggests that root test is easier. All right, so if I apply the root test to this, we're looking at the limit as n approaches infinity of the nth root of our expression. Everything's positive, so let me just leave off the absolute values. When I take the nth root, that's dividing the exponent by n. That's going to give me 1 plus 1 over n to just the n power. N squared divided by n gives me n. All right, so this is a very famous limit. If you don't know the answer, we'll go through it here. But as n approaches infinity, let's think about what this is. 1 plus 1 over infinity. That's 1 plus 0, which is 1. And then we have the infinity power. That's one of our indeterminate forms. So that's indeterminate. Here's the way we do that. So this is review back from the L'Hopital's rule stuff. If I want to figure out this limit, I have to do a different limit. I'm going to take this expression and apply the natural log to it. So I do ln of 1 plus 1 over n to the n by our, I want the limit of this. This is scratch work now, basically. And with the limit as n approaches infinity of the natural log of this thing, by the properties of natural log, I can pull the exponent out. As a multiplier. And now this limit is infinity times ln of infinity times ln of 1, which is 0. That's an indeterminate product. So infinity times 0. That's an indeterminate product. We handle those by rewriting it as a quotient and using L'Hopital's rule. So I want this to be ln of 1 plus 1 over n divided by 1 over n. Now this is 0 divided by 0. 0 divided by 0. So I use L'Hopital's rule on that indeterminate. And I was not counting on having this much space. Right. Derivative of ln of 1 plus 1 over n. That's 1 over the chain rule thing. So let's see. 1 plus 1 over n. Derivative of the inside is going to be negative 1 over n squared. That's also the exact same thing I'll get in the bottom derivative. So these will cancel. That will give me limit of 1 over 1 plus 1 over n as n approaches infinity. That comes out to be 1 divided by 1 plus 0, which is 1. Okay, so that was a lot of work. We got this number, but that doesn't tell us inconclusive because that's not the right limit that we were trying to compute for the root test. That 1 is the answer to the limit of the natural log of this. If I want the answer for this, I need to cancel that natural log with e. So my answer here is going to be e raised to the power that of whatever my answer was here. So e to the power 1. Because This function, this sequence, is e to the power ln of this. E and ln cancel. So if I want just 1 plus 1 over n to the n, I take e to the ln of that. Well, ln of that approaches 1. So this approaches e to the 1 power. E is 2.7, whatever. That's bigger than 1. So that tells us that the root test gives us divergent for our series. All right. So it's worthwhile to go back and review a little bit about indeterminate powers from the L'Hopital's rule chapter in chapter 4. I think it's chapter 4. Yeah. So it's worth reviewing that a little bit because those do show up a little bit in the root test stuff. But like I said, we're not going to be doing too heavy examples of these situations. Okay, so with the little bit of few more minutes in this video, let me just briefly address section 11.7. So 11.7 is about strategies for testing series, for testing the convergence of series. For our purposes, the problems I give you for series, for testing for convergence, I will narrow down your choices to which techniques I want you to use. Like, for example, if I wanted to use root or ratio test, I'd say, here's a series, use the ratio test or the root test. So you still have to decide between those two. Choose one of those to determine is it convergent or divergent or inconclusive. Or if I want to use a comparison test, I'd say use a comparison or a limit comparison to determine is it convergent or divergent. Or if I want you to use the integral test, I'll say use the integral test, or show that the integral test applies, and use the integral test to determine convergence or divergence. Or the alternating series test. So I'll narrow it down essentially to the section. But let me just kind of summarize our tests so far. So the first thing is the divergence test. We're looking at a series, summation of A n. And we're trying to answer the question, does it converge or diverge? If the limit of A n is not 0, and you easily see that, the divergence test tells us that it's divergent. So if the terms of your sequence clearly don't go to 0, then there's no point doing anything else. It's divergent. Now, if your expression is more difficult, if it does approach 0, or it's not easy to tell whether or not it approaches 0, then the divergence test might not help. But if it's easily seen to be non-zero limit, then you're done. Then, beyond that, we had, I'm not going to write the details for all of these, but we had two specific types of series that we already know the answers to. We have geometric series. If it's a geometric series, we can immediately say, does it converge or diverge? And even better, if it converges, we can actually compute its value. We also had P series, so that was summation of 1 over n to the P. And depending on P, we know, does this converge or diverge? So these are specific types of series that we know the answer for. Um, if a series is positive, so if the terms are positive and similar to one of these two, so it resembles a geometric series but with some extra terms, or resembles a p series but with some extra stuff in the fraction, so into the p plus some stuff in the denominator, then you can do one of these two. Use a comparison test or limit comparison. So if it's not too far off from one of these two, you can usually figure out the answer by comparing it to the appropriate series. Okay, so then the next thing, my thought process would be is the ratio test or the root test appropriate? Okay, so these handle specific types of things very nicely. Factorials, exponential expressions, other combinations of powers into the n situations. So these handle a lot of difficult things. They don't handle rational expressions very well, but rational expressions can be compared to p series easily. So the previous step in my strategy here would have been appropriate, if it was positive, of course. Okay, if these don't really work, then you're getting into the more specialized things. If it's an alternating series, you have the alternating series test available, where you look at the positive part and is its limit 0 and is it decreasing, then the series is convergent. So now you're starting to test things that aren't necessarily absolutely convergent, but rather conditionally convergent. But then after that, then you're getting into desperation sets in. Is it easily integrated? What I mean by that is the sequence you're adding up. If you turned it over into a function of x, would that function of x be something that you could reasonably integrate? If it looks like you could possibly integrate it with a substitution or something, then it's worth checking, would the integral test apply? And that's its own can of worms. You have to check all the conditions for the integral test. Is it a positive function? Is it continuous? And is it decreasing on an infinite interval? On an infinite interval. Right, so these are just kind of the brief guidelines for how you would approach a convergence or a series problem in the wild. So if you encountered a series and you wanted to know, does this series converge or diverge, and you don't know what section of a textbook it came out of, how would you go about thinking it through? Like I said, problems I give you, I will narrow it down to just one or two of these. Like I tell you, use either the ratio test or the root test on this problem, or use a comparison or limit comparison on this problem. Use the integral test on the problem. Use the alternating series test, and so on. You do need to know. So I erased it, but you do definitely need to know about geometric series, specifically, and you should also know about P series. And I'd also say alternating P series. That's worth pointing out. Alternating P series. That's one that you should know quickly because it'll be relevant in the next topic. So geometric series, P series, and alternating P series. Those three, you should know the answer almost immediately. Like we know by this point, the test will be open notes at this point since they'll be online. But you don't want to have to waste a lot of time looking up those answers when it should be something that's routine by then. Okay, so this will make more sense, hopefully, in the next topic. So next video, we'll talk about section 11.8, which is still talking about series, but now it's a specific application of series called power series. And that's taking these series and treating them as introducing a variable x to them. So they turn into functions of x. So we'll talk about those next time. So I will add a list of problems from section 11.6 over the ratio and root test. And the next quiz will be covering these past few sections, which will be homework and quiz number 8. All right.